moving on to the next part, case study of LRU-friendly workload. For workloads that use thrashing with LRU, both LIP and BIP reduce cache misses significantly. However, some workloads inherently favor the traditional policy of inserting the incoming line at the MRU position. In such cases, changing the insertion policy can hurt cache performance. An example of such a workload is the swim benchmark from the spec FP suite. Swim performs matrix multiplies in its kernel. The first knee of the matrix multiplication occur at half MB while the second knee occurs at cache size greater than 64 MB. Figure 7 shows the MPKI or swim as the cache size is increased from 1 by 8 MB to 64 MB under LRU policy. There is a huge reduction in MPKI as the cache size is increased from 1 by 8 MB to 1 by 2 MB. However, subsequently increase in cache size till 64 MB does not have a significant impact on MPKI. As we can see in the graph over here, as the size of cache is increasing from 1 by 8 to 1 by 4, there is not much change, but 1 by 2, uh, there is a huge reduction as the size is increased in the meshes. But increasing it further is not having much effect after 1 MB. Yeah, that's the thing. For the baseline cache, the MPKI with both LRU and OPT are similar in dictating that there is no scope for reducing misses over the LRU policy. In fact, changes to the insertion policy can only reduce the hits obtained from the middle of the LRU stack for baseline 1 MB cache. Therefore, both LIP BIP increase MPKI significantly over the LRU policy for the baseline cache. LRU incurs an MPKI of 23, LIP incurs an MPKI of 46.5, BIP incurs an MPKI of 44.3, and OPT incurs an MPKI of 22.8. So that here the LRU is more closer to the OPT. Well, we can also talk of the results. Well, let's talk of the results. In figure 8, let's see the figure 8. What is the figure 8? Okay, this is the figure 8. Comparison of static insertion policies, sent reduction in L2 MPKI. Okay, LIP BIP is 1 by 64 or like so. This is the diagram. Let's read the results. Figure 8 shows the reduction in MPKI with the two proposed insertion policies, LIP and BIP, over the baseline LRU replacement policy. For BIP, we show results for epsilon equals to 1 by 64, epsilon equals to 1 by 32, and epsilon equals to 1 by 16. What it means is that after 64, it is gonna put one element at MRU. After 32, after 16, it's gonna put the one element at the MRU. Otherwise, it will always place the element uh, at the LRU position. Which mean every 64th, 32nd, or 16th miss is inserted in a MRU position respectively. Okay. The thrashing protection of LIP and BIP reduces MPKI by 10% or more for 9 out of 16 benchmarks. The thrashing protection of LIP and the BIP reduces MPKI by 10% or more for 9 out of 16 benchmarks. BIP has better MPKI reduction than LIP for ART and AMMP because it can adapt to changes in the working set of the application. For most applications that benefit from BIP, the amount of benefit is not sensitive to the value of epsilon. For benchmarks, equate parser bzip2 and swim both lip and bip increase the mpkis considerably. This occurs because these workloads either have an LRU-friendly access pattern or the knee of the MPKI curve is less than the cache size, and there is no significant benefit for increasing the cache size. For the insertion policy to be useful for a wide variety of workloads, we need a mechanism that can select between the traditional LRU policy and BIP depending on which incurs fewer misses. The next section describes a cost-effective runtime mechanism to choose between LRU and the BIP. For the remainder of the paper, we use a value of epsilon equals 1 by 32, which is every 32th element is going to be placed at the MRU position, else it will be placed at the LRU position for all experiments with BIP. All right.